Hello and welcome back to our studies in physics. Last time we were talking about kinematics, and I've got a little summary of what we left with. So remember that we were beginning with just one-dimensional motion, so we were confining our object to either move just along the x-axis or just along the y-axis or just north-south or just east-west. In other words, only along one line. We already defined three quantities that we could use to quantify an object's motion, and one is position. And if we're just moving along one line and we just let that line be x for the purposes of this discussion, then the position of an object would be given by some location on the x-axis. So some position x for a final position, and remember that this little subscript naught is the initial position for an object. So this little naught is going to follow other quantities. It's always going to mean initial for that particular quantity. Then we define displacement. Displacement is change in position. This little delta symbol keeps track of the words change in. And we're going to be using this delta symbol again with lots of other symbols as well. And so displacement, change in position, final position minus initial position. Distance was another quantity that we covered, and it's just the total ground covered, how much distance was actually covered, and the symbol D is going to be used for distance. So now we're going to define a few more quantities, and with those quantities that we finished defining in this lecture, we will have all the quantities we need to be able to discuss motion, and then we'll start playing with them and seeing how they're related to one another. So time. Time is another quantity. We know objects don't stay in the same place all the time. So time is a quantity we're going to need to be using with these other quantities to describe motion for an object. Time's going to get the symbol t. And if we want to define the amount of time elapsed, then we would use the symbol delta t. So delta t would be some final time minus some initial time. Remember, all the initial quantities are going to have that subscript naught, and this is going to be the change in time. So again, the change in is shorthand notation delta symbol. So time is now defined for us. Another quantity that we'll need to become familiar with is speed. Speed's going to get the symbol S. And anytime we put a bar over a quantity, so now I've got a bar over speed, this is going to define our average speed. Okay, we'll be putting bars over other quantities as well, and that'll always mean average. So the average speed is defined as distance divided by the time that elapsed. Average speed, the distance covered or the total ground covered divided by the time it took to cover that ground or to cover that distance. Instantaneous speed will not have a bar on top of it. Instantaneous speed is going to be equal to the limit as we let delta t shrink down to 0 of the distance divided by the interval of time. So when we shrink this denominator down to pick out one instant in time, we get the instantaneous speed. Don't worry too much about the limit as delta t goes to 0, but this is the definition of the derivative that we'll be talking about a little bit. I'll be providing some context for people that have had calculus in their past, but don't worry, if you haven't, you won't lose anything. So now we have a definition for speed of an object. Another quantity that is not the same as speed is a quantity called velocity. So velocity gets the symbol v, and we're going to need to be very clear that these are not the same quantities, and we're going to need to be able to distinguish them. So again, I can define an average velocity with putting a bar on top of that symbol v. So this is average velocity. And this is going to be equal to the change in the position for an object. And remember, change in position for an object gets the symbol delta x divided by the change in time, or the time elapsed while the object was displacing it from its initial position to its final position. If I want to know the instantaneous velocity, well, it's in the same form. The instantaneous velocity doesn't get the bar on top of it, and it's the limit as delta t goes to 0 of the change in position over the change in time. So this is the instantaneous velocity. Now notice that in one dimension, this displacement could be positive and it also could be negative depending on what direction the object is moving. So let's say that I call the big I here in Albuquerque my origin, and I'm going to use I-25 as my x-axis. So heading north, I'm going to say, is going to be my positive direction. Heading south is going to be my negative direction. If the object moves so that its final position is more south than its initial position, then I'm going to have a negative value for delta x, and subsequently my average velocity will be negative. Notice that that's a big distinguishing feature between average speed and average velocity. Average speed can never be negative. It's just a distance, a certain amount of ground covered, divided by the change in time. And the change in time will always be positive. Time never goes backward. And so this quantity will always be some positive value. But the average velocity is not, that's not true. The average velocity could be positive or it could be negative. If the object ends up in a more negative location than where it began, then when I take the final position and subtract the initial position, I'll always get a negative value in the numerator. And again, delta t always being positive will make this ratio negative. So these two quantities are not the same. And remember, when an object changes direction, in other words, it turns around and starts coming back a different direction, then the distance traveled and the displacement are also not the same. So not only can these quantities have different signs, but they can also have different values as well. The last quantity we need to define to be able to fully quantify an object's motion is a quantity called acceleration. This one tends to be the hardest for students, and so let's really spend some time trying to make sure we get a good handle on it. We're going to use the symbol A for acceleration throughout the semester, and it's traditionally used across texts as A. And again, the average acceleration can be designated by just putting a bar on top of that quantity, and so this is average acceleration. Acceleration, average, is defined as the change in an object's velocity divided by the time that elapsed while the object's velocity was changing from some initial value to some final value. The instantaneous acceleration for an object is going to be equal to the limit as we shrink this denominator down to 0 and just pay out one instant in time, delta v over delta t. So the acceleration of an object is how its velocity changes with respect to time. So let's say you're on I-25 and you're heading south and you set your cruise control at 60 miles an hour. Your velocity isn't changing. You're continuing in the same direction at the same speed. And so your change in velocity is 0. In other words, if I start my watch right when I set my cruise control and then I stop my watch 10 minutes later, I still have the same velocity that I had before. In other words, my v final and my v initial are the same, and when I subtract a number by itself, I get 0. So it doesn't matter what the denominator is. If the velocity isn't changing, then you have no acceleration for an object. Notice that's very different than what your average velocity was during that same 10-minute interval down I-25. You were definitely displacing in space. Your position was changing in that 10 minutes as you were traveling south at 60 miles an hour for that 10 minutes. And so your average velocity is not going to be 0, but your acceleration will be 0 because there was no change in your actual velocity. These quantities are very, very different. Just like speed and velocity are very, very different. We need to be able to distinguish between all these quantities because these quantities are what we need to be able to describe motion for an object and are the study of kinematics. In the next one, in the next lecture, we're going to tie these quantities together and start looking at how we can extract information about one quantity by having graphs of other quantities, looking at graphical relationships. So one last thing I want to do before we leave together is just talk a little bit about units. In the scientific community, we use the metric system. And the standard unit for position in the metric system is going to be some position in space in meters. So x is going to have traditionally units of meters. Delta x, likewise, will traditionally have units of meters. When I'm putting brackets around a quantity, that means this is the quantity's units. What about time? What kind of units are we going to have for time? The units for time are going to be seconds, and abbreviated s. And I should clarify that the units for position are meters, but they're going to be abbreviated m. What about speed? The units for speed are going to be distance. Distance is going to be expressed in meters. Divided by time, time is expressed in seconds. So the units we're going to be using for speed, meters per second. What about velocity? What kind of units are we going to have for velocity? Well, displacement, which is in meters, divided by time, which is in seconds, again, meters per second. And lastly, what about the units for acceleration? What kind of units will we have for standard units in the metric system? Well, they're going to be units for velocity, which is meters per second, divided by the units for time, which are seconds. So we're going to have meters per second, or meters per second squared. So that gives us the units standard in the metric system for these different quantities. And these are all we need to be able to describe motion. Our task now is to fully understand them and be able to relate them to one another.